Yeah, it's the memory stupid. That's a quote from Richard Seitz, and he observed something in the 90s already, that the memory that is in our computers is kind of the bottleneck in the system. And still today, this is a huge problem, and that's my talk will be about today. So data is key for AI, right? So many important workloads are data intensive. They require rapid and efficient processing we have large amounts of data, so we can generate more data than we can actually process, right? So if we look on the GPT stuff, these transformer models, when we see how that started here with BERT in 2018, and then we had GPT-2 and then GPT-3, we see that we have an exponential growth in the memory requirements here, but also an exponential growth in the compute requirements. Yeah? So these are petaflop days. Crazy. Yeah? And here we have in gigabyte, that's still manageable, but petaflop days is an interesting metric. And more interestingly, GPT-4, they even do not disclose how large the model is and how many petaflop days they spend to train it. Yeah? So it's probably somewhere here, but I cannot tell you because they actively don't disclose it. And one big problem here is that this sentence doesn't work anymore. Yeah? I'm not sure if I should spend time optimizing my code or just wait 18 months for Moore's law to kick in. Yeah? So that's something what people did all the time. And now Moore's law is getting slower. Yeah? So we had actually two things in the past. So Moore's law is right now getting slower, and also Dennard scaling. The idea of Dennard scaling was that if we scale down our transistors in our chips, we can speed up or turn up the frequency. But this doesn't work anymore because of power. So the static power consumption of our chips is dominating. We cannot increase the frequency anymore. And what happened was, in 2006, Intel has introduced multi-core systems. Yeah? But this is not enough anymore. So if we look on a CPU, which could be a multi-core CPU, it's general purpose, right? So we can have specific applications here, and we can implement all these applications in software and can run it on the CPU, right? So pretty easy. CPU can do anything. Yeah? The performance is maybe not that high. For some applications, maybe more than for others. And also the energy efficiency. And if we compare that now with a graphic card, a GPU, then we can see there are some applications where the GPU works pretty good, which is graphics, but maybe also computations like Bitcoin mining. That works pretty good on GPUs, but there are some other applications that don't work very well on GPUs. And then we have so-called ASICs. And ASICs are application-specific integrated circuits. They are made for just one application or just a range of applications. And they are very energy efficient and very performant, but they are not flexible. So there are maybe ASICs, they cannot even add two numbers because they are not built for that task. They do maybe rapid calculations of the stock market or option pricing or something like that. And these accelerators, these ASICs, can be 10 to 1,000 times more efficient than general purpose CPUs. And recently, Hennessy and Patterson, they are analyzed in their Turing Award lecture that these ASICs have specific advantages. First of all, they can exploit parallelism, very good. They can make a custom memory management. And they can also deal with exact precisions. So this computer here uses 64 bits for floating point and also integers. But an ASIC I can build maybe with 17 bits. Yeah? So I just take the precision that I need for this application. And the other thing is DSL programming. So I can write my own custom programming language that is then compiled into a configuration for this ASIC. And this makes the computer architecture, again, an interesting topic, because in these areas we have to go. And one important area here is the memory management. And that's also the topic of my talk today. Yeah, so computing is heterogeneous nowadays. You find ASICs everywhere, even if you don't expect them. So, yeah, strictly speaking, a GPU is already some kind of ASIC. But we also have ASICs in the area of signal processing. We have ASICs that do cryptography. For example, in a flash controller, there are special circuits that implement security features, also error correction. Yeah, your smartphone, your iPhone, has already 60 accelerators in it. Yeah? So if you talk to Siri, basically, this is done with a special circuit. It's not done in software because it hears all the time. Yeah? So it's a special accelerator. And then we have AI accelerators, like NPUs or the TPU. And then, of course, Bitcoin mining. So it's not worth anymore to mine Bitcoins on normal CPUs. You have special ASICs for that. And then you read something in the news like this. Ja, Polizei macht unerwarteten Fund, Hanfplantage erwartet, Bitcoin mining farm gefunden. Ja. So, they expected some wheat plant there, and they found a Bitcoin mining farm. Yeah, so let's look on the TPU, which is kind of a monster, let's say. It's a special accelerator for machine learning. Technology is 7 nanometers, so that's the width of a transistor. And it has a performance of 275 tera operations per second per chip. And here you see that they have several of these chips on such a board. And these boards, they put together in a pod. Pod has 4,000 chips of that. And each chip has a thermal design power of 170 watts. And we have on-chip memory here. And we have HBM DRAM. This is a 3D integrated memory. And it has 1.2 terabit per second bandwidth, which is a lot. But we will see that this is not enough for the tasks that we want to run on these machines. Yeah, for example, Midjourney used the TPU to train their models. And if you see that, such one chip takes, in average, 170 watts, and then you have 4,000 of them. So I don't want to pay this bill to run a task a long time, right? So energy efficiency is also something which is really, really important. And the memory is often the bottleneck. So we have these huge number crunching ASICs here, and they are all limited by the bandwidth of the memory. We will see that in more detail now. So there is a specific model, that's the roofline model, that's how it's called, and it shows you basically what can your architecture of your compute system actually provide to you with respect to performance. And on the one axis, you have the operational intensity. That means how much operations I will basically execute per byte Yeah? And on the other axis, on the y-axis, you have the achievable performance in giga operations per second. So that means if you are in this area here, you are in the area of number crunching. That means you have enough, or you have a large locality basically on your data. So if you fetch 1 byte and then you make a lot of calculations on it, you will be on this area. So that means if your data is there and you can process on the data, then you are on this number crunching part, and you are only limited by the peak performance of your CPU. Yeah? So the maximum that you can get in giga operations per second is the maximum throughput that your compute engine can actually provide. Whereas if you're here in this area, then you have to wait for memory. So your operational intensity is low. That means if you fetch a byte, you make 1 operations on it, but then you forget about this byte, you fetch another byte and make an operation on it. Yeah? So the operational intensity is pretty low. So here you have high locality, and here you have the opposite. Your compute engine is waiting for the memory. And then, that's another roof line here, you have then a shape like this. Basically, if you are in this area, you are limited by the peak floating point performance. But if your application goes over there, then you are limited by the bandwidth. And here you see a gap. This available floating point performance cannot be achieved. And that's the roofline model. And for each architecture, you can draw different roofline models. Maybe for one architecture, it's more limited, and then it's here limited by the memory, and then limited here by the floating point performance, or maybe it's limited here. So that depends on the architecture. But now you can put applications into this graph. GPT-2, for this architecture where it was running, was here. And then when you run GPT-3, the number of parameters in these language models increases, right? And when you need more data, it's also somehow obvious that you move to this part, because you need more data, because you have more parameters. So GPT-3 is actually here. So that means that the performance of the GPT-3 training here is limited by the memory and not limited by the floating point performance. And this is a huge problem. Also that computing always scales faster than memory. We will talk about this, why this is the case as well. And it's the memory, stupid. And that's something that Richard Seitz already saw in the end of the 80s and then published in the 90s, that the memory actually was the bottleneck for the CPU, and the applications that run on the alpha architecture that he worked on were basically, I don't know how to say it in English, but in German it's Däumchen drehen. Yeah? So the CPUs just wait for the memory. So why is that the case? If we look back for 20 years, what the memory industry has done very good was increasing capacity. So it's normalized to around 2000 here. So we achieved 128x in capacity. Yeah? So it's not a big deal to go to a shop and buy 128 gigabytes DIMM of DRAM and put it in your PC. So that works. Yeah? What also is quite okay is the bandwidth. So we got an improvement of 20x of bandwidth in the last 20 years. But latency, what do you think happened to the memory latency? So what is the factor basically in improvements for latency? Ideas? Guesses? No, it's less. So memory latency stayed actually quite constant. And that's surprising. How can you achieve then 20x more bandwidth? Because engineers like me, they do a lot of tricks, and we fake a higher bandwidth with clever DRAM architectures. But the physics, that's where you see the physics, basically. The physics of the DRAM cell has not changed. It's the same thing as 20 years ago. And the latency and the frequency of the DRAM stays pretty low. Has somebody an idea what is the reason for that? So why is DRAM optimized that way? So the reason for that is basically this: cost, and cost per bit. Because if you buy memory, you don't buy speed usually, you buy capacity. So the whole process is optimized in a way that they can put as much as possible bits onto this small chip area. And the industry followed this line, but they completely ignored this one. So latency is slow. So we have to wait for the memory. Memory is horribly slow. And why is that the case? Yeah, because we always invested in the capacity, not in the latency. Yeah, and now it gets really crazy, and especially for computer science people, that's always surprising. Fetching operands costs more energy than computing on them. Or you always learn in the lectures, basically, that if you have computed a value, you store it to access it maybe later again. And now I tell you, probably that's not a good idea. Sometimes it's better to compute it again. A floating point operation on this 28 nanometer technology, so 64-bit double, you make an addition or multiplication or whatever, takes 20 picojoules. If you move this data from your registers in the CPU maybe to the cache, which is on the opposite part of the chip, this takes already 1 nanojoule. If you make then an access to the external DRAM, it's 16 nanojoule. So if you show that maybe to an accountant, the guy would say, yeah, it makes sense not to store things, just to compute it again and again. And Google has analyzed this. So in a smartphone, 62% of the total system energy is just spent on data movement and storage, which is pretty interesting. Yeah? So the architectures that we build, and also the architectures that you see here, that we divide computing and memory, which is there already since SUSE for Neumann, but for Neumann earned all the honors because the thing is called von Neumann bottleneck and not SUSE bottleneck, unfortunately. Anyway, communication is pretty expensive. Yeah, and the question that arises actually is, now we have this really cool and fancy number crunching machines here, and we completely move away from general purpose computing. So we build special chips for specific tasks. Yeah? And we don't use general purpose CPUs to compute things. So that's what we have. And the question is, why don't we have an application-specific memory system? Because most of the energy we spend in memory and communication, and also memory is hampering our performance. So why don't we have application-specific memory systems? And the answer is, again, cost per bit. Industry, or the DRAM industry, wants to tape out as many DRAM chips as possible with just DRAM cells on it, so capacity, and there is no business actually to run for special memories, because they just make the most of the money with the general purpose products. Yeah, so if I go to a memory vendor and I say, hey, I need an automotive DRAM, then they say, no, there's no market. The number of pieces is too low, too less cars compared maybe to smartphones and laptops. So, but before we now dive into this application-specific memory, let's learn a little bit about memory. So what is DRAM? And DRAM has been invented already '66 by Bob Dennard. That's this guy. And you see the structure of a DRAM cell in the background here. It's basically a transistor connected to a capacitor. And how is information stored? It's pretty easy. When the capacitor is charged, this is a 1. When it's discharged, this is then a 0. That's pretty much it. And we will look a little bit on the details, so how such a memory works. And he replaced actually the core memories. So maybe, have you seen them? No, okay. But these were basically these small ferrite cores, basically. And information is stored by inductance, basically. So it's the opposite concept. But he replaced that because it was possible now to put 1024 bits in such a small integrated circuit. So that's the circuit again of the cell. Data is stored by the capacity. We access the data with the transistor, and you can think about this like a bucket. So if the bucket is full with water, it's a 1. If the bucket is empty, that's a 0. And now we have a small problem here. We have a leaky bucket. So that means the information fades out, basically. So this memory is volatile. So first of all, if I disconnect it from power, then we will lose all the information. But this can take a long time. That's also interesting. I did some experience with that. But the cell is leaky. So that means we need, from time to time, to refresh the cell. So we have to look, is there some water in it? And if yes, we have to refill it. And this is what we call refresh, and this makes the memory dynamic. So we have to do housekeeping. We have all the time to check. Every 64 milliseconds, we have to check, basically, is there something in this cell? And if yes, we have to put some more water in it. If it's empty, we don't do anything. And how does such a DRAM cell look like in reality? So I have here a picture. So this is a normal transistor. And on top of this transistor, we put this stacked capacity. And now you can see something very interesting. So the ratio that you have between the width and the height of the transistor is in the range of 25 to 40x. So if you divide 2000 by 50, you end up in this area. So, and now my question is to compare that or bring that into a relation. You know the Burj Khalifa, the highest building that we have, right? What would you think is the aspect ratio of this building? So it's 140 and then 828, so 815 is pretty close. Maybe they put another antenna on top and then they gain some more meters. But you see the aspect ratio here is just 6. So you see that's a huge width here. So you see that this is pretty tiny, just 50 nanometers. So you can count actually the electrons, which are the charge carriers here. We have femtofarads in this capacity, which is really crazy. You can really count the electrons there. So that's how a DRAM cell works. And we learned already it's volatile and we have to refresh it. So how we build now a memory? We have here our capacitor, our transistor, word lines and bit lines, and then we put such a single cell, and now we create a structure. And the structure is called a subarray. That means we put 1024 DRAM cells here and 1024 up. So that's then our array. And why we do that? Yeah, because we want to do basically efficient wiring. So if we make just a huge array with several gigabits, the problem is that the length of the wires gets too long, and we cannot reliably sense anymore the data which is stored in the cell. And of course, the power would also be too high to drive these long lines. So what we do, we put them in these subarrays. And these subarrays we put again in bigger structures, which we call the DRAM bank, or DRAM banks. And we have here on these places preamps that are basically latching the data before we bring the data then later to the interface here. Yeah, and these DRAM banks can be used in parallel, but they share a common data and command bus, which is usually called DDR bus. So maybe you heard about that. This is how such a chip looks like. And now let's have a short look basically on the control of this device. So here you see again a zoom in of this subarray, which is located in the DRAM bank. And now the CPU can send to the DRAM a so-called activate command. And I show it again. The activate command will do the following. It will basically latch the data which is stored in one row of the cells here into this preamplifier. And that means now the DRAM is prepared. So I want to access data which is stored somewhere in this row of DRAM cells. And now the data which is stored here is copied to this preamplifier, primary sense amp, that's the correct name. And now I'm able to access the data. So this is just the preparation. And that's basically then the next command, which is then a read. So the CPU or the cache basically sends a read command. And of course, it can only read from the activated rows. And also, each of these commands takes some time. It's not important now to understand the time names here, but this takes time. So this produces latency. So when I send a read command, it's basically twice. First of all, I have to bring then from the primary sense amplifiers some of the data, not all of it, because this could be 1 kilobyte, for example. So I just bring some of these bits down there, which is then one DRAM access, which is 64 bits. Yeah? And I have then a DRAM bus, which is 8 bits wide. And then I have my 64 bits here, which are 8 bytes. And now I pipe the data here out, always in the packet size of 8, so 8 times 8 packages basically that I send out. So that's how the read command works. And this has two parts. This is the column latency. This is basically the time to bring the data down to the secondary sense amplifier, and then the time for the DRAM burst when I burst out the data to the CPU. Yeah, and then I have a so-called pre-charge command, which undoes everything. Yeah? So here, this is still latched. And now I want to access maybe data of a different row. Then I have to send a pre-charge command. And then this is basically a reset from the bank, and I can open another row. And also this takes time. This is the pre-charge delay. Yeah, and additionally, I can also open several banks in parallel. So I have some level of parallelism available here. So that's also important to note. Yeah, and then of course there is the refresh, and that means every 64 milliseconds I have to refresh each cell, and this is then done in a cycle of 7 to 8 microseconds, where I have to run through each of these cells. And of course the DRAM cannot be accessed by the CPU once the DRAM is in refresh. So that's another problem where we get huge latencies for our memories. Yeah, if we look now on latency, we see that an access to the same row in the bank is always better than have an access to a different row. So the idea is I open one row and then I do a lot of accesses there, a lot of read commands or a lot of write commands, and then I will be faster than changing the row all the time. Yeah? So you can see that here. First of all, I have to pre-charge. That means I close the row, then I have to open the row, then I can read data. And when I keep the row open for 10 accesses, then I just have to wait here 10 times t-burst. But when I now jump between two rows here, so maybe I start here with row 0 and then here with row 16,000 or whatever, when I jump from here to here to here to here, I always have to pay the penalty to close the row again and open it again. Yeah? And this is what you see here. So if I make 10 DRAM accesses to different rows, I have to pay 10 times the whole delay. Yeah? So then it makes sense if you make memory accesses to keep them in the same rows as much as possible in order to avoid this huge penalty that you have to pay here when you switch between different rows. And yeah, a row always has a huge penalty, and your latency will go up and your bandwidth will go down. Yeah? And additionally, we have the memory controller. So you have here your CPUs, GPUs, or your accelerators. And then there is a small circuit that actually controls the DRAM and sends these DRAM commands. And this is actually the bottleneck in the system. So DRAM controller transform read and write accesses from the CPU into these activate pre-charge commands and read and write commands. And the DRAM controller usually performs optimization during runtime. So if you have a pattern that accesses row 0, 1, 0, 1, the DRAM controller puts these requests in a buffer and then makes a reordering. So if you have the sequence of 0, 1, 0, 1, 0, 1, then the DRAM controller will first try to serve all the requests to the row 0, and then later all the requests to the row 1 in order to reduce the penalty that we have seen in the slide before. Yeah, and DRAM controllers must provide high sustainable bandwidth, low latency, and low power. That's their job. And they do that always during runtime by reordering memory accesses. Of course, they also have to make sure that no hazard occurs. Yeah? So if you, for example, you want to write something to the memory, and also later from the same location you want to read, and then the things get somehow unsorted, then bad stuff might happen. So the DRAM controller has also to track this and has to make sure that no hazards occur during this optimization. And then when I worked for one project together with an industrial customer, it was in the area here of medical image processing. It was a 3D scanner for your teeth at the dentist. And they had so much data that they want to process, and they had their first plan for the compute architecture. And their plan was to use 10 DRAM DIMMs. For each step in this image processing pipeline, they wanted to use another DRAM DIMM because they needed this high bandwidth. And in this regard, I came to the idea, why can we not make our memory system
more aware
of the application that runs. And that's where the idea started, actually. So you have many applications in embedded systems. This is food inspection, these medical appliances, but also for neural networks, especially for the convolutional networks, it's pretty interesting. Many applications feature a fixed or regular DRAM access pattern. And for neural networks, it's even the case that the pattern, how you access the memory, these images here, doesn't depend on the content of the image. Yeah? So you have a very deterministic access pattern in many of these neural networks. So we have this in image processing, real-time signal processing, and machine learning. And as I said, the access pattern does not depend on the data. And now we have our commercial off-the-shelf DRAM controllers that have only a local view on the application because they have this input buffer. The CPU throws in some requests, and the memory controller just sees what is in the buffer and does some local reordering. But if we know the big picture, basically what will the whole application do, we can do much better optimizations. Yeah, so the idea that I had was, let's build an application-specific memory controller which has the global view on the application, and I design it offline because I know what will run on this system. Yeah? So this system will never calculate bitcoins. Yeah? It's there for this medical appliance, and it's just built for this specific case. Yeah? So why not using an application-specific memory controller? And yeah, so how did we do that? So the question was, how can we place the data in the DRAM such that the number of row misses, so the huge penalty if we jump between two rows, is minimized? And when we look in the commercial DRAM controllers off the shelf, you usually see these kind of circuits. This is where the DRAM address, or the other way around, the CPU address, so the input address, is mapped to the rows, banks, and columns of the DRAM. So this is kind of a coordinate where we are in our DRAM chip. Yeah? And what is done very often, so the lower bits of your address are used for the column, and then in the mid, you have the bank bits that select which bank we are going to, and then the upper bits are used for the row. So for example, if you have now an application that just counts up the addresses, so you have a linear access pattern, the bits in the bottom will change a lot. This will change just from time to time, and the row bits almost do not change. And therefore, that's a good starting point, actually, if you have linear address patterns. Yeah? Because if the toggle rate of these bits is pretty low, you won't have, or you won't see any row switches. So you try to be in the same row as much as possible. And what you will find in Intel processors is this architecture. They do an address transformation here by using XORs, and they XOR some parts of the row with the bank. What is the result of that? The idea is the following: if you change the row, then you will also change the bank, because the new bank is calculated from row and bank together. So if you have a bit flip here, also this will change. That means you will jump to another bank and open the row there, and this is, for the average case, also quite good. But Intel is general purpose. They want to run a lot of applications, so they just take the architecture that in average makes the best performance, which is a fixed architecture like this. And in literature, I found then also some people that did address mappings like this for Fourier transformation and stuff like that. And in one of the first papers that I wrote on this topic, I did some kind of toggling rate analysis. I just checked, pretty simple for a specific application, which address bits actually toggle the most. And the bits that toggle the least, I just put into the row. Then I have also somehow minimized the number of row misses. But the results were not that promising, actually. So, and then I started to dig deeper. So what is the reason for that? And in general, you can say you have the CPU addresses that are mapped to DRAM addresses, and you can put any bijective function here to do a mapping. It must be bijective, that's of course clear. And my idea was we put in this mapping the application knowledge in order to minimize the number of row misses. And then we wrote the first paper about this. This was just a heuristic. Yeah? But my goal was to solve this optimal. So I want to find the optimal mapping. So in the sense of math, yeah, there is no better way to do it. And that was then the second paper, where we basically proved that this problem is unfortunately NP hard, as always. Yeah. But we found a clever way, and I was really happy to cooperate there with people from math. We found a clever way to solve that even for realistic instances of this problem, for real application. We have now an algorithm that is able to solve it. Of course, it has to run on a cluster, but it works. So what was the idea? The idea is basically pretty simple. I designed a circuit that is able to take a 32-bit address. Yeah, okay, I have used 32 bits. We have 64, but for the publication, it was enough to use 32 bits. So this circuit here is just a big multiplexer that is able to map each input bit basically to another one. And additionally, we have here the possibility to XOR some of the row bits here also with the bank bits. And then we have here configuration memory. And you can compute for this circuit here, you can configure 5 times 10 to the power of 11 different meaningful combinations. So now you can simulate your system this often, and maybe then you can also find the best mapping, but this won't work, especially not for 64-bit addresses. Yeah? So we cannot just do that by simulation, and therefore I talked to math people and they came up with an actually clever solution. And this I want to highlight basically today how we did this optimization. But me as an engineer, I'm really proud that this actually ended up in a real chip. So there was a cooperation with the University of Bologna and the ETH Zurich. And this memory controller, this application-specific memory controller has been taped out, I think 2 or 3 years ago. Yeah, so what is the idea? The idea is we want to exploit application knowledge. That means we want to exploit the determinism that we have in our application to find an optimal configuration that decreases the latency and also the energy and also increases the bandwidth. So we extract from our CPU the memory access pattern, which is basically a list of addresses and reads and writes. And we put that into our optimizer, which is called congen, second generation. That means just DRAM controller generator. And first of all, we do read and write optimization, but this is not the topic of the talk today. I want to talk about how we did minimization of the row misses. And we also do that, or we prove the result basically by means of simulations. And what is the output? Either it's VHDL code for a customized memory controller, or a configuration for a commercial off-the-shelf memory controller if it has a similar circuit like shown in the slide before. Yeah, but as I said, I want to focus in the talk only about minimizing the row misses. So every time, or we want to avoid to switch the rows if we access the DRAM. Yeah, and I just want to give you small example. So let's assume we have an artificial DRAM that has two banks, and these two banks we can access in parallel. And yeah, each of these banks has 8 rows, and then each row has 4 columns. Yeah? So this is a small DRAM. And if I want to build now the scrambling circuit, it will look like this. So and here it's much easier to understand how the whole thing works instead of the huge thing with 32 bits. So basically, each blue box here is one single DRAM access. Yeah? So that would be 64 bits, for example. And the question is now, how should we configure this circuit here such that the number of row misses is minimal? And for this small circuit, we have just 180 combinations, so we can also just try it out. But of course, we want to do that much more clever. Yeah, so let's assume now we have our CPU wants to access the addresses 10, 45, 46, 14, 60, and 34. If we translate this to binary, that would be the memory trace. So that's how we call it, basically. So these are the bits, and here you can see the 10, for example. Yeah, it's 8 plus 2. Yeah, so that's 10. Pretty easy. And as I said, the goal is now to find a mapping for these bits. So we have to permute them, and we also have to compute XORs such that the number of row misses is minimal. And how we did that? First of all, this XOR thing is a little bit complicated, and therefore we just enumerate all the possibilities that we have there. So if we look on this as a tree, we see basically, well, maybe here, yeah. So now we can see it. The first thing that we want to select is the bank bit. So we have now there 1, 2, 3, 4, 5, 6 possibilities. So this bank bit can be configured to be the A0 bit or the A1, A2, 3, 4, and 5. Yeah? So we could, for example, decide now that the A1 bit will be assigned to the bank 0. So we connect this to that. Yeah? And in the second step, we can then assign also here the row 0 bit, which is XORed with this bank bit here. And this is the important step, because with this XOR, this doesn't make the solution that nice. Therefore, we have to enumerate all the things in the beginning. But usually also for real instances, this always scales that we can still do that, and everything can be done in parallel. So the complete tree that we see here can be done in parallel. So if we, for example, decide that the bank 0 bit is connected to the A0 bit, then we are in this orange part in the tree. And if we then decide to have R0 connected to A1, then we would have this configuration, and we are also then here on this place where we have the orange dot. Yeah, and if I move one step further, then we would have this connection. A2 is connected to R0. Yeah? And so on and so forth. But for now, let's consider the situation here. So these 30 subproblems that we have, we solve all in parallel. This is pretty easy on a cluster. You can do that. And now I want to explain how we solve the rest of the configurations by taking this configuration where we have chosen A0 for the bank bit and A1 for the row bit. Yeah, so if we look at this, the first step is we have to XOR now the A0 bit and the A1 bit, because that was the selection that we did. And yeah, that's what we do. So we XOR those both, and we compute a new bank bit out of this. So yeah, you can see that XOR means basically they have to be different and then it's 1. Yeah? So you will have here it's different, you will have a 1, here it's different, you will get the 1 and here. Yeah? These are the same. So it's exclusive OR, yeah? Not the normal OR. And then you can see this is the new bank bit. And now we can start to permute basically. So what we do, first of all, since the banks are independent, we can also analyze them independently. And that's what we do. So we see here these accesses go into the left bank, these accesses go to the right bank. And then yeah, we order it in this way. The reason for that is yeah, they are independent, they don't influence each other. And that's the reason also why we can treat them this way. And now we can do an optimization independent of the bank bit. So it doesn't matter, the bank bit actually. And now we construct a corresponding hypergraph of this. And this means we see basically where are the changes in these bits. So for example, here we have a change in this bit from 0 to 1, and then again from 1 to 0. But here the bit doesn't change, but here it changed. So everywhere there's a change, I put that in a color. And now we have these 6 different addresses that we send to the DRAM, and I put them basically here into a graph. And the next step is basically always to mark this with a set. So this is the set for the first column, at which positions we have the bit changes. So here we have only one change for this set, and here we have here a change and here a change. So at 1 and at 0, then we also add this to the set, and so on and so forth. And what we now have to do is, basically we have to, in our DRAM we said we had 3 row bits, so we had 8 rows. So we have to choose 3 bits from those here, such that the number of row misses is minimal. And that's basically exactly the case in this configuration. So we have to choose 3 of these sets such that the total number of addresses in it is minimal. And then we solve the problem, and this problem is called K-min union. So that's what we do here. So if we choose basically these 3 sets and assign them to the rows, then we will have the minimum number of row misses. These automatically will be assigned to the columns. And how this problem is solved, it's done with the branch and bound algorithm. And in total for this example, we will have a minimum of 3 plus 1 row misses, so 4 row misses. And the first one, basically, you see here, this is when the DRAM is started and no row is open. And then the next row miss you will see here, because here there was no row miss because the row bits are the same. And here we suddenly have then a change at this bit, and this will directly introduce a row miss. And then we have the other row misses, basically also here, so we see 4 row misses, and that's the minimum. And this has been found by this branch and bound solver. Now we have this configuration, we can basically configure the circuit, but as you remember, we have to do this 30 times. So we find probably several solutions with a minimum number of row misses. And to find from them the best one for practical cases, so in this case we had 10 solutions, we put that into a simulator, and then we see basically where we get the highest bandwidth and the lowest latency. Some results just at the end. You can see that this is bandwidth for this 3D image processing from this medical appliance. And the first 4 columns here show the performance of the commercial off-the-shelf controller. So you see here with a pixel size and resolution of 8 bits, it gets 40 megabits per second. But if you increase the precision, you see that the bandwidth drops down. Whereas if you use this application-specific memory controller approach, these are basically the 3 columns on the right, you can see that with this approach you can always get almost the maximum bandwidth possible. Why don't you get the full maximum bandwidth? Yeah, because there's still the refresh that from time to time happens and then hampers your performance. For energy, we have similar results, so we are 1 order of magnitude more energy efficient. To summarize, we have a lot of challenges today. Dennard scaling stopped. Amdahl's law is kicking in. We cannot exploit all the cores that we have in our system. We moved to multi-core system because the single core performance was at its end. So this is spec-in benchmarks for single cores. We cannot increase the frequency anymore because our chips will burn otherwise. So we were forced to multi-core. But also in multi-core, we have Amdahl's law, which hampers us. Moore's law is slowing down. We have the dark silicon problem. We cannot switch on all the circuits anymore on our chip because it will burn. And memory and communication is one of the big issues. And of course, we also have a lot of opportunities. So we have to look at new approaches, new computer architectures like processing in memory, so processing the data where it makes sense. So there where the data is stored, we should also process it and not always shuffle it from memory into the CPU and back all the time. That means also non-von Neumann architectures, neuromorphic computing, quantum computing. And of course, there is a high potential with application-specific memory systems. And I hope I could give you an idea how such a system could look like. That's not the only solution. That's just one solution that worked pretty well for a specific class of applications. But I think it's worth to go in this way. And as Hennessy and Patterson said, it's a new golden age for computer architecture. Thank you very much.